Hi, I'm Nicole Schuman, the Agriculture and Natural Resources Extension Agent in Goochland County. I'm going to be walking you through some information related on how to actually interpret that soil test result when we get it back from the lab. I'm going to start with the most practical piece, which is what to actually do with those fertilizer recommendations, because we get a value for nitrogen, we get a value for P2O5, we get a value for K2O in terms of how many pounds per acre of those nutrients we need to be applying, but that doesn't actually tell us how much fertilizer to put out on the ground. If you have someone who's doing a blend for you to get those recommendations exact, or if you're having you hire someone else to apply, they have to worry about that. But if you're doing it all yourself, you need a little bit of math to actually translate those values of nutrients into the pounds of fertilizer product you need to put out. Just as a side note, the recommendations that come off the soil test are in terms of P2O5 and K2O instead of elemental phosphorus and elemental potassium. Your fertilizer analysis, if you go and look at like the label on a fertilizer bag, those are also in terms of P2O5 and K2O. Just want to make you aware they're different from the elemental forms of that nutrients, but the recommendations and the fertilizer analyses are both in the same terms. So just a little side note, if that is complete gibberish to you, just disregard it. You don't have to worry about it. But to get us started on our example here, we're gonna say that we have an acre of watermelon that we're trying to fertilize. Soil test results came back and said that we needed 90 pounds per acre of nitrogen, 150 pounds per acre of P2O5, and 150 pounds per acre of K2O. Easy enough, right? Except you can't just go to the store and find a fertilizer and an analysis that's like 9, 15, 15. So we have to figure out a way to work with what we got. And in this case, let's say we're able to get our hands on some DAP, or diammonium phosphate. So a common analysis for DAP is going to be 18-46-0. So that means it's 18% nitrogen, 46% P2O5, and it has no potassium in it whatsoever. So we're using our DAP, we're going to try to fulfill our P2O5 recommendation. I always set these problems up as like a proportion or a ratio. So on one side, I'm going to put whatever's in the bag, and then on the other side, I'm going to put whatever winds up on that field. On the top half, I am going to put, so my numerator, I'm going to put whatever the nutrient is. In this case, it's P2O5. And then on the bottom, I'm going to put whatever the product is. So in this case, that's going to be DAP. So based on what I have here, I know how much P2O5 I want to end up on my field, right? That's my recommended amount. So my 150 pounds per acre of P2O5, I'm going to place right here. What's in the bag? I know that as well because I have that from the fertilizer analysis. It tells me that it's 46% P2O5. So for every 100 pounds of DAP, that will contain 46 pounds of P2O5. So 46 over 100 goes on my left-hand side, 150 goes on my top over here, and then that all goes over X, because this is the amount that I don't know, right? I don't know how much DAP I want to apply to my field, but I'm trying to figure that out. We don't have to go into the algebra too much, but we'll just go ahead and cross multiply. So 150 times 100 gives me 15,000. And then if we do 46 times X, that gives us 46X. We want to get X by itself in order to figure it out. So we divide both sides by 46. My 46's cancel over here, leaving me with X. And 15,000 divided by 46 is going to be about 326. I'm going to round here. We don't have to worry too much about the decimal places. So I need about 326 pounds of DAP per acre. And that will satisfy my P2O5 recommendation. So we're good there. Now, let me scooch this over so you can see it. Now, we need to figure out how much nitrogen we just put out, because DAP doesn't just have P2O5 in it, it also has nitrogen as well. So we're going to say, for our nitrogen, what I have in the bag, what I have on the field, and then nitrogen is my nutrient up here, and we're still talking about DAP, of course, here. So there are my proportions. So in the bag, we know that DAP is 18% nitrogen, so for every 100 pounds of DAP we put out, we'll put out 18 pounds of nitrogen. In the field, we already know what we're going to apply, right? We're going to apply this 326 pounds per acre of DAP, and we really want to know how much nitrogen does that end up supplying. So we go ahead, we cross multiply. 100 times x equals 326 times 18. 326 times 18 gives me 5,868. Then to get x by itself, we divide by 100. So x equals about 59, again, I'm rounding, gives us about 59. So when we put out 326 pounds of DAP per acre, we end up putting about 59 pounds per acre of nitrogen. But that's not our entire nitrogen recommendation, right? We need 90 pounds per acre. So if we do 90 minus 59, that gives us about 31, right? So we need an additional 31 pounds per acre of nitrogen. Thankfully, we're able to get a hold of some urea. And a common analysis for urea is going to be about 46,000. So it just has nitrogen in it. There's no P2O5, there's no potassium or potash in it at all. So if we're gonna, I'll probably come over here to just set up that equation. So in the bag, on the field, again, we're still talking about nitrogen. In this case, we're looking at urea. So in the bag, urea is 46% nitrogen. For every 100 pounds of urea, there are 46 pounds of nitrogen. On the field, we need 31 additional pounds of nitrogen. So we're going to put 31 here. We're going to put X here because we don't know how much urea to apply. We cross multiply. We get 3,100 equals 46X. We divide by 46 in order to get that to cancel. And then, so 3,100 divided by 46 gives us about 67. So we need 67 pounds of urea per acre. And that will get us, between the DAP and the urea, that gets us all of the nitrogen and the phosphorus that we need to satisfy that soil test recommendation. But we're still missing our potassium, right? So maybe we then go and we get a product like potassium sulfate, which the analysis on potassium sulfate is normally something like 0,050 plus 18. The 18 is any sulfur that's contained in that product. So we'll go ahead and set up, again, just one more proportion where we've got our K2O on the top, our potassium sulfate on the bottom. This is our bag. This is our field. K2O, we have 50% K2O in our potassium sulfate. So for every 100 pounds of potassium sulfate, there's 50 pounds of K2O. On the field, we need 150 pounds of K2O, and we're not quite sure how much fertilizer to apply. Cross multiply equals 50x, divide to cancel the 50. That leaves us with x equals 300. So we need 300 pounds of potassium sulfate per acre. Now, if you're feeling like you're getting the hang of this and you want to do a little bit more, you can go ahead and try to see that when we apply that 300 pounds of potassium sulfate, how much sulfur do we end up applying with that recommendation? So you can set up your proportions and solve. If you run through those calculations, I will tell you the answer just so you can double check. You should find that we put down about 54 pounds per acre of sulfur if you run through those calculations. So all in all, we need to apply 326 pounds of DAP per acre, 67 pounds of urea per acre, and 300 pounds of potassium sulfate per acre in order to satisfy those recommendations. When you get a report back from Virginia Tech's soil lab, it's going to look something like this: a soil test report from a private lab. If you test through just a different service, it'll come back looking a little different, but it generally contains a lot of the same information. As we already discussed, we've got our fertilizer recommendations in terms of pounds per acre, and also our lime recommendation down there at the bottom. We already talked a little bit about how to take those from something that's written on paper into something that you actually apply to the ground. I think before we delve any deeper into what's actually on this report, it's important to think about kind of our plant food pyramid. You've got your primary macronutrients: nitrogen, phosphorus, and potassium. These are consumed in the largest quantities by plants, and so they're the base of the pyramid. They're the most important. Following that, you've got calcium, magnesium, and sulfur, still consumed in fairly large quantities by plants, but not as much as nitrogen, phosphorus, and potassium. And the cherry on top, of course, are those micronutrients. They're normally found in small quantities in soil, but they're also consumed in small quantities. Of course, kind of the foundation of the entire pyramid is actually pH, because our pH is pretty critical in determining nutrient availability in the soil. So generally speaking, I actually look at pH first before I look at anything else when I get a soil test report back. In this case, soil pH is probably a little bit low, but not necessarily atypical for a soil that we would find in Virginia. And that pH is going to have a determining effect on that lime recommendation. However, it's not the only thing that goes into that lime recommendation. The lab also takes into account the buffer index, which you find right next to that soil pH. Buffer index is kind of a tricky concept to wrap your head around. You might just want to think about it as the soil's ability to resist a change in pH and leave it at that. When I learned about buffer indexes and the buffering ability of soils in school, they liked to use the metaphor of this coffee dispenser. So if you picture two coffee dispensers side by side, they both have a tube on the outside that kind of measures the level of coffee in that dispenser, but the reservoir could be any size, right? It could be larger or it could be smaller. And so if you go and you pull just an 8-ounce cup of coffee off of my big reservoir and off of my small reservoir, you will see like a change in the level on the tube on the outside. We can think of that as our active acidity. Because the coffee dispenser that has the smaller reservoir has sort of less coffee in reserve, you actually see a measurable change. You see the level in that little tube drop, whereas our coffee dispenser with the big reservoir, you can't see much of a change. The big reservoir is akin to a clay soil here. The smaller reservoir is akin to a sandy soil. It's kind of a, I don't necessarily know that this is really helpful for people. It's just how it was taught to me. Something that may be more useful for you is a metaphor I came up with, which are, you can think about two trees in your yard. Maybe one of them's older, it's 25, 30 years old. One of them's a sapling you planted last year. Fall's starting, the leaves are starting to change and turn colors, and you walk outside and there's, underneath both of these trees, there are 5 leaves. And you say to yourself, oh, there's 5 leaves on the ground. I have the same amount of work to do to rake these leaves up. And, if your wife says, oh my God, you're an idiot, obviously you're going to be raking for longer underneath the big tree because it has the ability to drop leaves for longer than that small tree does. So that's, you can think about that as the bigger tree is more like a clay soil where it has more leaves or more acidity in reserve. And so it'll take more work, it'll take more raking, it'll take more liming to actually neutralize the acidity of that soil. Not sure if that clarifies anything. If it doesn't, just ignore this part. So between those two, the soil pH and the buffer index, we get our lime recommendation. Normally that is in terms of tons per acre. We end up applying quite a bit of lime to soils in order to get that pH where we want it. We also have CEC, or cation exchange capacity, right next to buffer index. CEC is a measure of the amount of attraction between soil particles and positively charged elements, which would be cations, also known as cations. The units here are milliequivalents of charge per 100 grams of soil. And we look at CEC in order to get an idea of the soil's ability to hold nutrients against leaching. Generally speaking, we see CEC values in Virginia between maybe 1 and 12 milliequivalents per 100 grams, just based on how weathered our soils are, the types of clay minerals that are typically found in them. Normally, clay soils are going to have a higher CEC than sandier soils, just because they have more exchange sites for those little cations to hang out on. Then we also have acidity and base saturation right next to CEC on that soil test report. So if CEC is telling you how much capacity there is, how many cations you can hold with your soil, acidity and base saturation are telling you the composition of those cations. So how many of them are acid-causing cations and how many of them are basic cations. Your acidity is going to be things like hydrogen ion, of course, because that's actually where pH comes from. But it could also be things like aluminum that contribute to acidity. Base saturation is going to be your calcium ions, your magnesium ions, and your potassium ions all together. If you look at those values, they all sum up to 74, which is our base saturation. And of course, our base saturation plus our acidity sums to 100. So it accounts for 100% of the exchange sites in your soil. We've also got organic matter. This is not part of the basic soil sampling package. However, it is something that some producers are interested in looking at, especially if they're doing like vegetable production or something. You may also be interested in looking at organic matter if you're maybe you're switching to a new production system, so you're going to no-till, or you're changing how you're doing your grazing. You're probably not going to see changes in organic matter just year to year, but it may be that over the course of a decade or so, you can see measurable increases in that organic matter depending on how you're managing the soil. Organic matter is important because it actually controls a lot of soil processes. It tends to have a high CEC, so it can help with retaining nutrients, cycling those nutrients. So some people are interested in looking at it. Typical values for Virginia might be anywhere between 1 and 4 or 5% organic matter. We don't usually see values much higher than that unless it's something that's had significant organic matter deposition for many, many years, maybe a ton of manure and mulches and other things like that added to the soil. Now we get to go on to the good stuff, which of course are those nutrients, right? So you have your result for each of the macro and micronutrients looked at in the soil test. And that is just a straight up measure of how much the lab found in your soil. And even though you only submitted maybe a cup of soil, the lab reports those results in terms of pounds per acre for your primary and secondary macronutrients. And then it reports results in terms of parts per million for your micronutrients. You also have a rating for each of your results. And the rating is actually based on how your soil test result compares to what the crop you want to grow needs. And that is based in part, of course, on whatever it is you're going to grow, because different plants have different nutritional needs, but it's also based on the yield estimate if you provided one to the lab, or if you didn't, it's based on the productivity group of your soils. So how much can we actually expect a given crop to yield on your soils? Then they work backwards from that. They say, okay, well, then we would expect, so much potassium, so much phosphorus to be taken up by that crop. And do you have enough in your soil to actually support that level of crop removal? So the rating is going to tell you, it also just gives you a sense of like, are you going to see a crop response to fertilizer? For levels of low to medium, you're pretty likely to see a response to a given fertilizer for that crop. For a rating of high, you're probably not going to see a crop response. However, the lab still may recommend a fertilizer application just based on crop removal, just trying to replace whatever the crop is going to remove during that growing season. So for our phosphorus, potassium, calcium, magnesium, that's all going to be, those ratings are going to be low, medium, or high with minuses or pluses. For our micronutrients, it's just going to be sufficient or insufficient. Just a quick note on parts per million and pounds per acre. So 1 acre of soil to a 6-inch depth is approximately 2 million pounds. So 1 ppm out of, 1 part of 2 million pounds would be about 2 pounds. It would be 2 pounds. So to convert ppm to pounds per acre, you multiply by 2. To convert pounds per acre to ppm, you would divide by 2. It's not rocket science. If that doesn't make any sense to you, disregard. But as you can see, our micronutrients are reported in ppm. And in part, that is, that's because they're found in pretty small quantities in the soil anyways. As you can see, for this soil test, all of our micronutrients were at sufficient levels for crops. Generally speaking, the best way to manage micronutrients is going to be just to manage your pH. Normally, there are enough in the soils. It's just a matter of whether or not they're available to plants. I do sometimes get producers who will be looking over their soil test results and they're like, well, what about my micronutrients? And I'm like, well, your pH is low and, your soil test ratings aren't great for like phosphorus and potassium. So let's fix those issues before we talk about anything to do with your micronutrients. Generally speaking, what's going to be limiting in the system is those macronutrients and the pH. So It can be important to look at micronutrients in certain contexts, but they're typically not the first thing I worry about when I'm looking at a soil test. Here is calcium, so one of our secondary macronutrients. Values for Virginia tend to range between like maybe 700 to 1,400 pounds per acre. And of course, we don't normally recommend like a fertilizer application for calcium because we tend to put a lot of calcium into the soil just when we lime. Lime is calcium carbonate, generally speaking, so it's got calcium in it. Right next to calcium, we have our magnesium. And again, with magnesium, we typically add magnesium when we lime. A lot of the lime in Virginia is dolomitic lime, so it's going to have just some magnesium content in it naturally. If you had a calcitic lime, it would just have calcium, but generally speaking, we've got dolomitic lime, so you end up adding magnesium when you lime. Some people, you may encounter this on the internet or just other producers, some people think that the ratio between nutrients matters just as much as the quantities of those nutrients. That isn't something that we've seen supported by the research. So they might tell you, oh, you need to balance your calcium and your magnesium ratios. Generally speaking, the research has demonstrated that as long as you have more calcium than magnesium by a ratio of about 2 to 1, you're good to go. Now, phosphorus. So on to those primary macronutrients. Phosphorus is found right here. And then, of course, our fertilizer recommendation in terms of P2O5 rather than elemental phosphorus is found down here. As I've said before, fertilizer labels will always be, and their analyses will always be in terms of P2O5. So that fertilizer recommendation will correspond directly to the fertilizer bag label without any need for conversion. But there is a difference between elemental phosphorus and P2O5, but you don't need to worry about that if that sounds like complete nonsense to you. Here's our potassium, similar story with our potassium and or our elemental potassium and our K2O. And then we have our nitrogen recommendation right here. If you have a pasture of some sort, the nitrogen recommendation might be this little comment down here. It depends on the percentage of legumes in the stand. Now you may be wondering, there's no nitrogen test result on this on my soil sample results. Why is that? And that's because nitrogen tends to be really mobile in soil, just based on its chemistry. Nitrate leaches pretty easily because it's an anion. So you might take a soil sample test in the fall to prepare for your growing season next spring. And by the time you get around to the spring, that nitrogen level is going to be completely different than whatever you tested in the fall. So it's not usually useful information. So those nitrogen recommendations are just derived on crop removal rates and what the crop generally needs. It's a similar story for sulfur. So if you were playing along, you may have noticed that sulfur was listed as one of those secondary macronutrients, but it doesn't appear anywhere on our soil test. And that's because, like nitrogen, it tends to be just really mobile in soils. And also, historically, we got a lot of just well, I won't say natural, but we got a lot of just atmospheric sulfur deposition through basically acid rain. Now that we've cleaned up the air quality quite a bit, we're seeing much less sulfur deposition than we have historically. So we're slightly more likely now to run into an actual sulfur deficiency in our field. Typically, those look similar to nitrogen deficiencies. It's just like a yellowing, a chlorosis of leaves. If you think you have a sulfur deficiency, go ahead and take a tissue test. That's going to be way more accurate than a soil test. At telling you if sulfur is an issue. Sulfur is also sulfur can also be tested for pretty easily just out in the field by just sprinkling down a little bit of elemental sulfur. And if you see a crop response, then yeah, you could probably benefit from a sulfur addition. But because there's not like a well-defined relationship in the research between sulfur soil sample test results and crop response in the field, we just don't bother testing for it. We don't bother reporting on it. I hope this information has been helpful for you, and please reach out if you got any questions.